Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first.
Thank you, Anna, for introducing the session. A very good day to everyone, and thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying Meng from ITU, International Telecommunication Union. Today, we're excited to host another webinar titled The Future of Internet of Things and RF Intelligence Through Large Language Models. The Internet of Things, IoT, and RF systems are entering a new era, driven not only by better connectivity, but also contextual understanding, reasoning, and adaptability. In this talk, we will discuss how LLMs can bridge the gap between human intent and machine execution, low-level signals and high-level insights, and the applications of LLMs as optimizers and interpreters within the context of IoTs. But before officially kicking off the session, I would love to introduce our esteemed speaker, Lina Beria. Lina Beria is the adjunct professor at Khalifa University, the founder and lead of Women in Machine Learning and Data Science Abu Dhabi chapter, and also the adjunct research professor at Western University. And my colleague Vishnu, who will be taking care of the Q&A session. Now, without further ado, please allow me to pass the baton to Lina. Lina, the floor is yours.
Thank you so much, Jiaying, and the rest of the AI for Good team for having me in this session. It's my honor to join you and to present my talk on IoT and RF intelligence and their interplay with large language models. Allow me just to share my screen. Yeah. You can see my screen?
Yes, we can.
Thank you. So let me first introduce myself briefly. I'm Lina Beria. I'm a scientist from Khalifa University. I'm working mainly on the intersection of AI and telecommunications with a particular focus around large language models, generative AI, and how we can incorporate them into different aspects of telecom and network intelligence. And recently we have identified a new venue, or it's not a new in the sense of IoT is not a new, but it's a new vertical where we can leverage large language models and large-scale Gen AI in order to deliver more user-centric services that are controlled and driven by the users. Now, we have seen how LLMs have been changing different fields, and what we are sure about is that LLMs has a huge potential when it comes to IoTs. And this is due to the fact that IoT applications by nature are more user-centric applications, and then utilizing the capabilities of LLMs and how they are capable of understanding a human language in these surfaces actually makes sense. So we already started to see some fundamental changes when it comes to IoT, how they are operating, how they communicate, and how they understand us. So in my talk, basically, I will discuss what we believe will be the next major step in LLMs and in IoTs, and how we are using large language models to transform how our physical environment interact with us and optimize themselves, but at the same time, how we can interact better with our environments in a more meaningful way. So before going further, what is next and how LLMs will somehow change this era of IoTs, it's important to understand how we got here actually. So the IoT started as a purely industrial concept back in the 1980s. And the goal was very simple: connect machines to the internet to improve automation, to improve efficiency, and so on. At that time, it wasn't called actually IoT yet. The term IoT actually was coined officially with the emergence of RFID technologies around the 1990s. And it was aimed for supply chain tracking. And this was somehow the first real development toward what we call networked intelligence and physical systems. And then the radical change happened around the 2000s, where IoT started to enter our space and to have applications that are oriented to the users. So we started to see it in our homes. We started to see smart thermostats, connected smart lighting systems, wearable devices, some early personalized healthcare tools. And here where we started to see more tangible applications of IoT that are changing our lives. And why I'm emphasizing on this one, because later on I want to explain why this is not actually enough and why we need to look for more personalized and user-centric applications when it comes to IoTs. And then more advanced, so when I'm talking around LLMs, it's not like the first time we are using LLMs with AI or machine learning. And all these advancements happened with a combination of IoT and wireless evolutions. Now, at the heart of IoT evolution is the advancement definitely of wireless technologies, which have been definitely a key element in the development of IoT systems, starting from 3G, which provided basic foundation for mobile internet access, which was what we were looking for from IoT back then, enabling some basic IoT applications with limited data transmission capabilities. And then we had 4G with better data rates, lower latencies. And then here we can have more complex IoT applications. So we started to see real-time video streaming, data analytics, and so on. And finally, now we have 5G networks with advanced cloud and edge computing. And here we introduce more ultra-low latency, improved capacity, and connecting massive number of devices simultaneously. Now, as I mentioned, this is not the first time we are seeing AI definitely with IoT. It has been well studied over the last couple of decades. So AI began to appear as a tool to improve IoT systems sometime in the 2014s. And it allowed these systems to learn, adapt, make some decisions locally. But most of these AI systems that we see with the advancement happened around them are basically narrow, in the sense they are trained for a specific task that we aimed for when we trained that model. And they are trained for particular environments that are dedicated for that model. And any changes with these environments or tasks, the model will fail. And that's why they were not flexible enough, and they were not actually built for open-ended interaction with the users. Now, let's talk about where things stand and why current IoT systems are not yet where they should be now. We always describe today's IoT systems as connected. We describe them as smart, but the reality is that they are not really intelligent within the concept of intelligence that we are looking for or we understand these days. They are still very limited in a very fundamental way. And so from one perspective, they heavily rely on manual configurations, meaning that most IoT systems still rely on applications, drop menus that we use, predefined rules. So they are very limited in terms of adaptability. Second, we have also the intelligence associated with IoT systems is actually narrow, as I mentioned. Even when machine learning is used, it's trained on a single task or a single scenario. It doesn't generalize. And this is a very important aspect if we're looking for massive deployment of IoT devices with some kind of level of intelligence. We need to ensure that these AI models and these devices can, AI models deployed at these devices can generalize. At the same time, current AI models or machine learning models cannot reason. It doesn't adapt to new user needs without further retraining. This is a huge limitation when it comes to IoTs. Now, third, when we are dealing also currently with as we mentioned, I would say networked intelligence and IoT. So we have IoT devices dealing with connected to each others. We are dealing with some kind of fragmented devices and protocols. So a sensor from vendor A most of the time doesn't talk very well to a controller, for example, from another vendor. So we end up with a complex and a costly system, and such kind of limitation will limit us from scaling these applications to further applications and services. Then there is also raw data overload. IoT systems, we know, generate massive volumes of sensory data, but there is no tangible insights or actions that can be taken from IoT data. The majority of the data actually is really underutilized. So we have a lot of data. We use it for a particular task that these models are trained on, and the rest of data and whatever it adds in terms of context are actually not used or utilized in a good way that we can benefit for different applications for the future of IoT. And then a key aspect, especially when we talk about user-oriented systems and systems that are driven by users' demands, there is a huge limitation in how we interact with these systems. There is no conversation, no understanding. IoT today talks to itself, not to us. Humans at the moment are outside the loop. Even if you are setting like your watch, you're setting something in your mobile phone, you are still using some predefined applications, some particular drop menus that you need to use in order to communicate your request to IoT device. There is no conversational type of connection between the humans and IoTs. And later on, I will show you why this is actually very important and why we need this type of conversation and why LLMs particularly are useful in these scenarios. Now, finally, in terms of limitations, the user experience currently is uniform. So everyone gets the same logic, the same interface, the same defaults, regardless of the contents, regardless of my own intents, regardless of the user preferences. We all have, for example, our phones optimized to charge overnight, the same way, with the same logic. We all have in all rooms the same thermostats that are used to adapt ACs into a particular room temperature that's set by the system and so on. They are all working together. And here we ask ourselves, what if IoT can understand what we want, the way we see it? What if we could translate our individual intents into actions through the help of large language models? So here, just before moving to discuss further on how LLMs can help and how can change this IoT systems, I want to emphasize that why it's important to give the control to the user. Basically, because every user in the network or every user in our environments, they have different demands, different requirements. The space around them are different. So when we give the users the tool to control their environments to their needs, we enhance the quality of experience and we allow the users to tailor their environment to their specific needs, optimize their costs in a way that's suitable for them, optimize for energy consumption, data efficiency, and then we make these environments more sustainable and personalized. So large language models, as we know, originally built for text generation and conversation, but their capability to understand the human language is well suited to solving key problems in IoT systems, as we discussed in a few minutes. So having a natural language interface, meaning no applications, no menus, just talk to your LLM. You say, for example, make it cozy for reading. And the system interprets that into a series of action across, for example, your lighting, your temperature, the noise around you. So LLMs will enable some kind of bidirectional understanding, meaning that it's not just about us telling devices what to do, it's also about devices telling us what's happening in natural language. So you get, for example, human talking to a device, more control from human to the devices through an LLM, but also we have devices talking to human, and here more utilizing the data and getting more insights through using LLMs and getting more benefit of the data that these devices are introducing, but also making these IoT devices more proactive and providing us information that we might miss to get and so on. Also different than rule-based systems, LLM can use historical context, user preferences, and even like sensor data to make more adaptive decisions. And here we eliminate the need for manual rules. No more of this, then do that logic. And we shift into intent-driven behavior. So user intent-driven behavior, where the system understands what you are trying to achieve and figures out how to get there dynamically. So at the moment, given the limitations of LLMs, we can achieve the step where LLMs can understand what we want and can suggest for us some tasks or actions. What we are looking for in the future also to have LLMs more like action models, not just language models that are incorporating these actions for us as well. That's where we are calling for more agentic architectures or agentic LLMs. Now, we have already seen a couple of advancements when it's coming to developing powerful large language models that we saw in the last, I would say, 3 to 5 years, no more, it's like 5 years. So in addition to these developments, we started to see other trends in LLM research that will help this vision of LLM IoT becomes a reality, and then we can achieve it. So first, we are seeing the fast increase in multimodal large language models. And as I mentioned, when we're talking about IoTs, it's way beyond textual data. Now, understanding human and textual data is very important and is a key factor of why we are considering LLMs for IoTs. But it's not sufficient, because when we're talking about IoTs, we have images, we have sound signals, we have sensory data, we have RF signals, and that's all contribute to the insights and the information that we need from these IoT devices. Also, there is an increased interest on sustainable generative AI. So we understood here that LLM performance is not just about scaling. It's not about having bigger models, bigger data sets, using more compute for better efficiency, but also about the efficiency in sense how much value you get from every token, every watt you are consuming from power. And this is very important for energy-aware environments like IoT systems with all the constraints in terms of resources they have. And then we have LLM-based coding, like tools like Devin. There are, I'm sure, many others that appeared after this one within the similar capabilities, but these tools show how LLMs can reason with logic, how they can write codes, how they can configure systems, because when we're talking about any kind of engineering systems, at the end, it's a code that needs to be written and executed. So having these LLMs capable of doing these ones helps us a lot in the background, how these LLMs will be capable of executing and configuring, planning, controlling the different tasks when it comes to IoT systems. Now, on the deployment side, which is also an important aspect for IoT, edge LLMs are now becoming something very hot topic at the moment and becoming actually a reality. We are seeing models that run on smartphones, microcontrollers without needing the cloud. This is very critical when it comes to latency and privacy that IoT systems usually demand. Another important aspect, which I will focus later on, is the fact that LLMs are not just generators. In fact, they are becoming optimizers and controllers. And we will discuss in more details around this topic further. And actually, I'll be focusing my topic around how LLMs can be utilized as optimizers and controllers. And the final trend here, as I mentioned, we are moving into agentic architectures, where an LLM can be part of a modular pipeline that sense, reason, plan, decide, act, and so on. Also, in a couple of slides, we'll explain why we need this multi-LLM agents, why we cannot use a single LLM, or at least at the moment, we cannot rely on a single LLM, and why we need multi-agent architectures in order to realize this vision of IoT. So these trends actually confirm that we are not just building conversational agents as it started with LLMs, but rather layers of intelligence. So these trends are in line with the different layers of intelligence that OpenAI has defined recently that needs to be achieved in order for us to realize AGI, or artificial general intelligence. So the first layer, it's the one that we are familiar with, and it's a kind of well-matured one at the moment. It's about generating responses, understanding intent, interacting in natural language, and it forms actually the interface layer between the devices and the humans. Then we have the reasoning AI. This is where models go to solve problems, generating logic, plans, providing explanations, and then we move into the third layer of having autonomous agents. And here, models are not just answering, they're, as we mentioned, they're acting. They take goals, they break them into tasks, they use tools, they access some kind of needed APIs, and so on, in order to implement the actions that they suggested to solve a particular problem. After that, we have innovating AI. This is where models can combine ideas, explore even new solutions that the model that we don't have at the moment, or the model we're not trained on, and even generate like new strategies if needed. And then finally, we have the organizational AI, and this is more around the coordination layer, where we have multiple agents or models collaborating, manage large-scale operations. And this is where AI can act as a system of systems. Now, relating to IoT systems, especially when talking about RF environments, we need intelligence that covers all of these layers, understanding a user request, reasoning about, for example, signal interference, autonomously optimizing devices' behavior, and so on. And all these topics can be put in the concept of large perceptive models that we recently introduced, or also we can refer to it as large ambient models, which are basically models that understand the ambient. So models that can read from the environment and express to the environment. Here, the role of LLMs goes into two directions. First, LLMs as interpreter. And here, where the physical world talk to us in a natural language. So IoTs talking to us, utilizing different data modalities to give us more insights from our environment. And here we have two modules, or two different agents. First one, an understanding agent that need to process different data modalities, reason across them, and get insights and solutions. And then we have the communicating agents, which is a little bit simpler agent, which basically tasked to convey the insights that the first agent have to us in a different way. It can be in a textual way, it can be by an image, it can be by an audio playing, and so on. So it will be the interface between the agent that perceived the information, the process this information, and between us to understand in our own language how these, what's, for example, the optimum thing, if there are any insights, and so on. So for examples here we have multiple ones, but if we're talking, for example, about energy optimization problem, an LLM can read, for example, current energy levels, the consumption over the last couple of days, and then compare and reason, and then communicate with you, for example, some energy demand. So here, for example, we have energy demand up 15% versus last Thursday, likely due to inefficient batch processes, distribute load, like it's asking you if to distribute. The same, for example, for some IoT devices, like we have AR/VR latency up to 12 milliseconds, backhaul congestion detected, switching to edge processing, and so on. So it's analyzing what's happening in the environment, suggesting some reasons why this is happening, and then suggesting also actions, what you need to in order to solve this problem. So, and then we have the other way. So here, the IoT is talking to humans. Now, the other way, LLMs as optimizers, here we have humans talking to IoTs through LLMs, expressing their personalized needs. And LLM here understand the intent and constraints imposed by the user, formulate it into a mathematical problem, and then solve or call a solver, and at this point we'll discuss it later, to find the solution for the problem. So for example, if you, for example, talking to IoT, you say, minimize my energy bill while keeping the temperature below 24 degrees. So here the large model recognizes the goal, what you are looking for, which is minimizing your energy bill, understand the constraints that you are putting, which is keeping the temperature below a particular value, and then formulate the optimization problem, and then generates a time-based schedule of how you want to run this, for example, energy part. Here I want to also emphasize on this constraint point. So traditional systems usually don't allow users to impose their own constraints. As I mentioned, we have a uniform user experience, meaning that, so taking the example of your phone charging. Now, my iPhone, I receive sometimes this notification at night. It has this feature of slow charging until, for example, sometime in the morning to be fully charged, to optimize somehow, to maximize battery lifetime or whatever objectives or constraints they have. Now, these constraints are not imposed by me. These are not my requirements. These are constraints put by the manufacturer. Now, how we see LLMs changing this? For example, for me, I want the same problem of charging, but I want to optimize for cost. I don't care about, for example, at the moment, for the battery lifetime. So I want to charge my phone until morning, but make sure to charge during the time where electricity prices is low. I can even add more saying this, but also make sure not to fluctuate a lot because I want to keep also my battery life longer. Now, this is my constraint. Other user might prefer to have optimized for example, faster charging, particular time. If it is conventionally 6 a.m., I want, for example, to have it fully charged at 4 a.m. instead of 6 a.m., regardless of the price, regardless of the battery lifetime, and so on. So here we are shifting from some kind of predefined rules that are actually initially aimed to be user-centric, but fail to accommodate the individual users. So it provided some kind of uniform experience for all users. And it became less personalized and did not deliver the individual needs. And now the LLMs, we believe this is possible and can radically change the way how IoT systems are designed and operated in order to meet this, let's say, personalized requirements. Now, what kind of use cases these large language models as interpreters and optimizers can realize? So let's take this first one, which is around understanding RF signals, which opens up several useful applications, not only from telecom perspective, but also from user perspective. So this can play a role in different applications within IoT, user-centric IoTs. So traditionally, RF signal analysis is handled through metrics like signal strength, frequency, amplitude, phase, and so on, which are actually reliable, powerful, and they are performing very well when it's around understanding the RF signals, but they are also low level and they're purely technical. For a human to make sense of them, you will definitely need some domain expertise and a lot of manual interpretation. So for example, here in this one, as an example, we have a traditional signal heat map showing where interference might be happening, maybe near a reflective object like a cabinet here. What LLM is bringing to the table here is more contextual interpretation. So I don't need just to read this. I need to be an engineer to understand what is this heat map is telling me. But in this case, if I'm using an LLM, this system not only observe like there is signal degradation, but explain why, and it can also suggest some actions to be taken. So it might say something, for example, we have here signal degradation. This is most likely due to some reflective interference. Consider moving the sensor 2 meters away. And then by combining our signal data with some semantic inputs, like a description of the space or a floor plan, the model can understand both the signal patterns, the physical context, and then give you more insightful feedback of your environment with some actions that you can take in order to enhance particular area that you are looking for. Now, another useful use case can be on environment mapping, meaning the ability to understand the physical space, objects, layouts, how they evolve and change over time. In traditional system, we use, for example, LiDARs. We use RF signals to measure, for example, the coverage. We can use cameras to detect objects. The role of large perceptive models here is to integrate these different modalities into a single semantic map of the environment. So in this example here, we have the large perceptive model receiving data from all these inputs, like the RF signals, RF sensors, LiDARs, cameras, and so on. It detects an increase in, for example, device density in zone B. It can be, for example, a meeting room filling up, so it starts to detect some kind of higher density, and it responds proactively in this way. For example, device density in zone B is increasing, recommend reassigning channels and adjusting beamforming. This has huge potential, not just for IoT, for wireless networks, for robotic navigation, for context-aware automation, controlling smart spaces, and so on. So it goes beyond just one single application. It extends to different verticals and systems around us. Now let's see something more, I'd say, human-centric, which is intent-driven optimization. So instead of configuring a large number of settings as a user, users simply express what they want naturally, like in natural language. For example, I want to say, make my space cozy for reading. Here, a large perceptive model can interpret this intent, like what I want from this one, and figures out what actions, for example, dimming the light in that particular way, lowering the temperature to that particular temperature, for example, activating or activating some kind of noise cancellation, possibly even recommend some kind of reading list. So it depends on how you configure it or what you're looking for. It will provide for you all these kind of actions that are provided given your request. And this is a real shift from just automation into more intelligent environments. And this process is not just, for example, here I'm providing this example of comfort, but it can scale up, as I mentioned, to any engineering system: energy saving, bandwidth control, some kind of scheduling, smart grid load balancing, and so on. So it depends, but it all goes around understanding your intent, your objectives, what are your constraints, and then giving you the optimum solution according to that. So here we are switching it in a different way. So in conventional systems for optimizations, we are giving the user to control the parameters in order to get the outputs. Here we are giving them to control the outcomes. So what you want, and then we let the large perceptive models to take care of the rest of the operations, optimizing the parameters, of solving the optimization problem, and so on. So here, just to more emphasize on the multimodality part. So everything we have seen so far, from signal interpretation, user optimization, and so on, direct us to an important point, which is the ability of large perceptive models to go beyond text and the need for these models to go actually beyond text. So as I mentioned, LLMs started with language, but the real breakthroughs and the tangible outcomes we noticed, or this happened when we integrated multimodal inputs and outputs, when we started to see these visual models, audio models, and so on. Models that can understand things like wireless signals, 3D positions, environment context, information, and so on. This is what we are looking for. And then through carefully designed large perceptive models, we can go from, for example, having wireless signal to some kind of 3D environment reconstruction. Then we have here improved sensing, object detection. Another way, we can go from 3D positions to some kind of predicted trajectory. This is beneficial for localization, movement prediction, and so on. Finally, if we have, for example, we can go the other way from environment context back to wireless signals. Here, definitely we open several opportunities of optimizing beamforming, handover, interference avoidance, carrier scheduling, and so on. And this is what we call all-sense integration. Here we have the full spectrum of digital senses. So we have sound, sight, touch, which can be acquired through some haptic feedback, pressure, temperature. We have taste, we have smell. And then we have tying them all together through semantics. And now if we have a large perceptive model operating at the edge, combining and aligning all of these inputs in real time, it can see, it can hear, it can feel the environment, it maps this into some kind of semantic communication, it generates insight, generates captions for you, it decides some actions and so on. And here IoT system do not just like detect data from systems, from sensors, but actually experience the world in a way that we are experiencing it, or the way how we are perceiving that information from our environment. So here, just to show a quick example of what can be achieved through LLMs with Internet of Senses or all sense integration. I will not spend much time, but just to give you a general idea. So here we have our aim. This was done in partnership with Aalto University. Our aim was how we can remotely navigate a drone. Drone, following the IoT constraints, they have limited resources. So having needing to some kind of video streaming all the time in order to navigate in a very low latency while an energy efficient manner is very challenging. So we thought if we can deploy an LLM at the UAV in a way that once we have an image, it converts that image into just a caption or a prompt. And then we communicate this prompt instead of communicating images and videos. And then at the controller side, we have another LLM that will take this prompt and then convert it into an image from the description provided at the prompt. We convert it into an image, and then the remote controller can actually navigate the drone. Now we can see in this application, like in terms of fidelity, it's very, it's not as high fidelity as the original one, but actually it's providing you the main element that you need to navigate a drone. So I don't need the fine details of a tree. It's sufficient for me to know there is a tree with these dimensions in order to navigate my UAV. And this is another thing that we can play around in order to optimize these LLMs for IoTs. We don't need to have all features that we need, but we need to make sure that these LLMs capturing the features that we need. So this is just to show how we can incorporate these LLMs with different senses. And here also we considered the temperature. So from the image, it can give you like how the wind is moving, what is the approximated temperature, and the accuracy was really high. And this is also helpful when you are navigating a drone, like how the wind or the direction of the wind, what is the temperature, so you can navigate in a better way. Now let's go to the core concepts that I have been talking about, how we can use LLMs to understand, optimize, and so on. So can LLMs actually optimize? So the whole concept is tied to the fact that LLMs to be able to formulate and solve a constrained optimization problem. So can we do this directly? As a matter of fact, and unfortunately, no. Currently, large language models are not yet ready to replace traditional, sophisticated optimization engines. They struggle when the number of variables becomes large. And in these scenarios, they often lack the precision, solid algorithmic accuracy that are needed to solving complex optimization problems. However, I want here to emphasize that the strength of LLMs here is that they can interpret user intent, they can structure input data, they can explain results, and they can sometimes assist in defining the optimization problem itself, which are very important factors for enabling user-driven IoT systems. So how we can utilize these capabilities to enable LLMs to be as interpreters and orchestrators for IoT optimization. Here we defined 3 directions. First way is to train an LLM or take a pre-trained LLM and fine-tune it on optimization data, meaning that we build data sets for diverse optimization problems, the way to solve these problems, the solution for these problems, and then fine-tune the model. Here we have a couple, of course, of limitations. First, building such a data set can be very challenging, and then ensuring that the LLM can reason enough through the solution is not clear yet. On the other hand, one of the main purposes of leveraging LLMs in IoTs is actually to accommodate scenarios which are difficult to be formulated in a mathematical way. Yet these directions, like, I'm not saying that this is not a direction that we need to pursue, but still yet to be studied. Now, the second approach is through a collective intelligent way where we utilize multi-agents which coordinate, play some games to optimize a particular objective. Here, the main concern is on the convergence, generalizability of the policy, and so on. Now, the last approach, which we actually studied and we believe LLM can make a big difference here, is the integration of LLMs with traditional solvers. So the LLM understands the user intent and know how to connect the optimum solver and choose which solver needs to be used for this particular problem. So here we have the LLMs handle high-level tasks like problem formulation, interpretation, if there are any constraints, to generate these constraints, and then pass this to a traditional solver for computation. And this is why we introduced this multi-agent LLM architecture. And that's why I mentioned at the beginning that this multi-agent architecture is needed at the moment in order to utilize LLMs in IoT devices. Because currently, a single LLM cannot actually handle this issue of solving an optimization problem. I'll spend some time here just to explain the 3 agents that we are proposing in order to structure LLMs as agents within an optimization pipeline. So the goal here isn't for the LLM to solve the optimization problem alone, but to act as a bridge between human intent, mathematical formulation, and solver execution through some kind of a modular multi-agent systems. So let's take this example and understand the different rules of the agents given this example. So I have here the example that we are using for energy management scenario. So I want to minimize my EV charging cost while ensuring my car is fully charged by 7 a.m. in the morning. Now, this agentic architecture allows most technical IoT problems to be solved through 3-step methodology. First, model the problem mathematically. So this is the user input converted into a mathematical problem. Estimate the parameters that are needed of that mathematical problem, and then use the model to optimize the decisions. And this optimize the decision depends on either to solve or to call a solver. Now let's go back to the example and see after the user will send the request, how the different agents will handle this request in order to optimize for the user objectives. So here we have first the user will send the request, which can, and what we did is to have it through a voice request, meaning that the user will talk directly through voice messages. And this request will be sent to the first agent in our architecture, which is the modeling agent. This agent job is to take natural language, which can be, in most of the scenarios, can be vague, can be incomplete, can be informal, and convert it into a formal mathematical description. Because usually the user will give a request that might not be very clear, incomplete information, and this agent with the LLM capabilities need to understand these intents, objectives, constraints, requirements, and convert it into a formal mathematical description that can be used by the rest of the system to optimize for this energy problem. Now, this is where our approach is different significantly from existing frameworks. So other methods assume that the problem is already fully defined in a mathematical form. But in real-world IoT systems, users do not speak in equations. They speak in goals, things like keep my home cool while, for example, minimizing the cost, or track my energy while like doing a workout and so on. And then the modeling agent must extract the clear goals, variables, constraints from this language and build a usable mathematical model. Now, one of the most important design aspects here is the accessibility of the parameters. So the model only includes parameters that are either sensed by the environment or explicitly provided by the user in the request that the user gave. For example, if a user wants to track energy while, for example, doing some kind of weightlifting workout, but doesn't mention that I have this weight for the dumbbells, and the system do not have any access to sense this weight, the agent will omit this information. So it cannot provide what's the impact of the dumbbell weight on this optimization problem or on tracking this one, and so on and so on. And this ensures that the model is both usable and grounded in the system's actual capabilities. It's not like providing some superficial constraints or some kind of superficial goals. Now, the second agent in our architecture is the estimation agent, and its job is to fill the gap between the model and the real world. So the modeling agent gives us the structure of the problem, and the estimation agent fills in the missing values using data from IoT devices, sensors. If there are any external sources we are providing the system, then this estimation agent will get these values from these sources. In some cases, it can be through analyzing raw sensory data. So here the rule is mainly to extract from the user request and the system sensory data the needed values and parameters that are required for the particular optimization problem defined by the modeling agent. Now going to the last agent, which is the decision-making agent, which is basically the engine that takes the fully formed problem with all the parameters and find a solution. Users usually want to optimize something. Can be minimizing cost, can be saving energy, can be maximizing device or battery lifetime, and so on. So agent 1 models this goal in a mathematical way. Agent 2 estimates the parameters, and now agent 3 needs to solve it. This agent receives either, it can be formulated as an optimization problem, it can be optimal control problem with some kind of defined objective functions, constraints, if there are any boundary conditions, any system dynamics, and its job to find solutions that are feasible and optimal given these requirements and given these objectives and constraints. Now, there are two possible approaches here. First, using classical numerical solver. So here the LLM can interface with optimization libraries using tools like code interpreters, but it doesn't just run the solver, it also choose which optimal solver to use based on the problem class that I received. It can help with tuning the hyperparameters like the step size, the initial conditions. It monitors and adjusts the solving process dynamically as it sees how's the output coming, and so on. So here, the LLM defined the optimization problem, defined the class. The rule of this decision-making agent is to connect to the optimal solver and help to optimize this process. The other way is to use an LLM itself to approximate the solution, meaning that use LLM to solve the mathematical optimization problem. And this, as we said earlier, still in its early stages. But recent research has shown that LLMs can sometimes solve small dimensional optimization problem directly by some kind of reasoning over sequence of numbers, patterns, constraints, and so on. So the most robust approach today is some kind of hybrid, combine classical solvers with LLM-driven reasoning. Now, we have tried to build this multi-agent architecture and to try it for some kind of IoT application. And here we are making it more user-oriented. So here my colleague is talking to an LLM. I will run the video now, but just to explain the background, talking to an LLM, asking for some requests regarding charging the battery, regarding heating the water, regarding the temperature of the room, and so on, in order to allow the LLM to optimize. Now, this is still an early stage work. So basically, we deployed this through even WhatsApp application. So through a voice message, she is talking to the LLM through her mobile phone, asking for the request that she needs. The LLM will process this optimization problem and will provide some kind of energy map over the coming couple of hours. So here, because we still don't have the advanced LLMs to implement, but our aim here to show how LLMs can actually understand user intent, formulate a constraint optimization problem, solve this problem through connecting to a solver, and give you the optimum, for example, energy vector for the coming couple of hours to achieve the objectives that you asked for. So I'll just run it. I think it's just 1 minute or less.
I will come back home at 8 p.m. Make sure the apartment temperature is 20 degrees, that I can take a shower with hot water, and that my EV is fully charged.
Now she gave the request and the LLM started to process. At the end, maybe it will not be very clear. That's why I put it here. It will show on her WhatsApp the power vector or the energy vector that are planned by the LLM. Okay, so that image, the white one, it's basically this one, which is the optimum energy vector. Now, of course, we have several challenges that we face when integrating LLMs into IoT systems. So starting from mobile edge generation, this remains definitely a major challenge, as running LLMs on resource-constrained IoT devices require balancing real-time performance, reasoning capabilities, energy efficiency, and so on. Also, we have LLM deployment for IoT, here another constraint, and it's constrained by the reliance on cloud and resource efficiency. That's why we need lightweight, like task-specific models that reduce latency, ensure privacy, optimize for on-device resources, and so on. Another point is communication, meaning LLM to LLM communication and LLM to device and device to LLM. And that is why we require reliable, some kind of standardized methods for LLMs to interact with each other and with the devices. Another key challenge is multi-user adaptation. So now here we considered one user, one environment. There is no other user imposing another constraints. And here, if we want to deploy it for a multi-user IoT system, we need to ensure that the LLM can adapt to conflicting preferences between different users, especially when we are in a shared environment, and to accurately link each user request to the correct context, to the correct device, to the correct priorities, to the correct solver, and so on. So scaling this at a larger level of multi-users also constitute a challenge. And finally, tokenizing and representing physical IoT data for LLMs. So traditional tokenization methods struggle with raw and numerical inputs, and this is why we need new approaches to insert data in a meaningful way for effective LLM processing. And here I'll stop my talk. Thank you all for listening. I hope I'm within the time limits.
Hey, thank you very much, Tina. I think thanks for a wonderful talk. Audience can, of course, ask questions in the neural network, but I have some superpower, so I will use the power to ask you some questions anyways. I think your point about the IoT talks to itself. I think I can kind of generalize it to say that, the network itself is a bit preoccupied with itself. I think the networks typically don't talk to us. It's basically
No.
quite preoccupied. So I think that's a wonderful concept. I think one of the important points that you touched towards the end is the standard protocols, interface protocols. I think you mentioned the need for protocols for the LLMs to talk to each other and the devices. And if you see your figure, I think if you see your figure, you did call out the interface with multiple external, for example, the optimization libraries that you call from the I think it was the decision-making agent, for example, calls the optimization libraries. I think this kind of interfaces are quite important for standards. What is I know that there are some protocols now, for example, model context protocol. They are currently existing, but from your research, from your experience, your research, what are the characteristics of these protocols?
So it's two things. Either we have, as you mentioned, like a standardized protocols in order to enable LLMs to communicate to each other or to communicate to humans, or actually to leverage more, I would say, emergent protocols that are developed by the LLMs themselves. Now, this is definitely a huge topic. I'm not really actively working in this area, but just to maybe shed some lights here on the decision-making agents and how it interacts with the optimization libraries. So here, basically, we are building it more as, I would say, a classification interface in the sense that we are providing this optimization library. So we know, for example, in such scenarios, we will have these optimization problems. These are, for example, the top 10 major optimization classes that the LLM can face. And then we are providing the different solvers for these optimization problems. We are building this library, and then basically we're asking the LLM to act as a classifier to use, depending on the optimization problem that are identified, the optimum solver for this problem.
I see. Okay. I think that's an interesting answer. I think depending upon the type of interface, you think that typically there could be generated interface, maybe discovered interface, and this type of very niche type of interfaces that you explained as well. It's interesting. Okay. I want to ask you about the large perceptive model. I think you explained very nicely. It looks to me that these are different collection of different models, different types of models potentially. And I want to ask you about the fine-tuning aspect. I mean, the context-specific fine-tuning. I think just taking your example, I believe the enterprise, indoor, outdoor type of use cases will require different types of models. For example, a factory floor is different from my studio, for example. So I think that kind of specific fine-tuning may be required. So my question is it really a collection of different, do you see it as a different collection of different types of models? And in that case, is there a role for this type of specific fine-tuning based on context?
Yeah, so yes, as you mentioned, it's not just a single model that we are building. And so large perceptive models is more like a concept than a single model that we are running. And that's why I emphasize the need for the multi-agent architecture. And each agent can actually have different LLMs with different, I would say, capabilities. Some can be just textual models, some can be visual models, some can models to handle more like unstructured data and so on. So, and building these models, now we can use for textual ones and so on, we can use some kind of general purpose models, but it's always recommended that you fine-tune the model based on the application that you are considering. And so, for example, now here when we built the not exactly for this video, but we had a prior work that was a bit simpler. So what we did is we provided kind of few short examples for the model to allow the model to focus its knowledge more around EV charging, because the problem that we considered at the moment was around EV charging. And in order to ensure that the model can understand the terminologies of EV charging, the requirements, the problems that usually are faced for EV charging. So we provided kind of few short examples as a knowledge base to the model to allow it to understand these concepts. So I agree with you that each model, if you need to use it for a particular scenario, so either in terms of fine tuning, which can be sometimes costly, but if it is a simpler, I would say, application or a simpler model, then you can provide kind of a knowledge base for future examples or for kind of a RAG application where the model can better understand the context of the application that you are considering.
Yeah, I think that's quite interesting as well. There are few research directions which maybe actually I'll come back to you on the future directions. But let's come back to data. So you mentioned that data part a little bit. I think you mentioned the energy optimization use case. I think you had a nice figure on the signal coverage optimization also. And my question is that around the data requirements and the model requirements, I think there are specific data sets required for each of these. Maybe there are specific model requirements just now we discussed. So what would be the role of IoT in this? I am guessing that probably it plays an important role in building up this data context and then doing some stitching together. I'm not very sure. So I want to ask you, the data requirements, the data format requirements, structured, unstructured, and so on. What is the role of IoT in this whole data set business, Shivan?
I'm not sure if I'm getting your point correctly. So, but if I understood it properly, so IoT will be the source for generating the data. Now, in terms of what kind of, I would say, data, this depends on the application. So in terms of whether it's textual data, whether it's RF sensory data, and so on, visual data, this depends on the application that we will need. So, and depending on these applications and the models that we have, then the data set need to be like defined and developed. I'm getting your question correctly.
Yeah, I think that's what I meant as well. So once this is done, we need to look at maybe fine tuning or optimizing the models based on the data sets and formats. Is that what you do?
Either it's fine tuning or, as I mentioned, like RAG application or knowledge base, some kind of support and so on. So yes, like for each application that you're using, you will need some kind of data set, whether to fine tune the model or to allow the model to speak that data, the language of that data.
Interesting. So there are typically these videos, these webinars are seen by upcoming researchers. So I want to finish off maybe with this question. I think I can see several very exciting research directions. I think you already mentioned a couple of them. I think the standards interface part itself is quite interesting. This perceptive model and fine-tuning knowledge base, these are all very exciting fields. Real-time aspect is, I think you had your last slide where you had called out a couple of directions.
Yeah,
Those by itself, yeah. So yeah, those by itself are quite important directions. But I want to ask you, what are the future directions? What are you going to, let's say if we were to host you next year, what are you going to talk about?
I think it's more around moving into large action models, because so at the moment we reached this step where we are optimizing and we have, let's say, the optimum solution. But that's it. It's like the human needs to implement that solution, especially when it comes like we have this energy vector, and then we need to optimize to implement it for my energy system. Then I need to go and configure the system to, for example, charge at this time, do this one for this, and so on. So how we can somehow build some kind of APIs or more action agents that are capable of implementing and deploying these solutions into my system. And here we will realize this automation in the system. But also in terms of one of the important aspects for the multi-user adaptation, because it's now within your house, you can somehow control it. But if you are going outside the house, then we will definitely have different conflicting outside preferences and constraints coming from different users. So how we can scale these LLMs, these agents, to be able to accommodate the different needs? Do we need like to have additional agents that are somehow responsible for classifying the user preferences, finding some kind of overlap between them, and then pass it to the other agent to develop the optimization problem? This is yet like to be well understood.
Really, yeah, it's really exciting. Yeah, I think we look forward to your future research as well. Thank you very much, Lina, for patiently answering all the
right.
discussions and points. Yeah, back to you. Yeah, back to you, Jay.
Thank you so much.
Thank you, Vishnu, for the Q&A session, and thank you, Lina, for your contribution during the whole talk. Now, I would also like to thank everyone for watching this webinar today. We encourage you to stay until the very end and interact with our speaker online. We'll have more interesting talks in the future, so please check the AI for Good program page for more details. We look forward to seeing you in the future. Thank you for joining, and have a nice day.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.